Welcome back to The Explainer. I am absolutely thrilled to get into today's topic with you all. We're going to break down one of the most powerful concepts in mathematics, a rule that essentially acts like a cosmic detective. You see, calculus isn't just crunching numbers or solving abstract equations. It's fundamentally about uncovering hidden truths in the physical universe. Today, we're exploring the mean value theorem.
To kick things off, let's look at a real-world physics mystery. It's a paradox that might honestly make you rethink your next road trip. Imagine you're cruising down the highway, you pass a police radar gun, and you're totally under the speed limit. A while later, you pass a second radar gun, and again, you're perfectly under the limit. Yet a few days later, a speeding ticket arrives in your mail. How is that even possible? How do you get a ticket if neither radar actually caught you speeding? Well, it turns out math can solve this without any direct observation of the crime.
Let's walk through this journey step by step. So, step 1. Your car passes radar A going 55 miles per hour. The speed limit is 60, so you're fine. Step 2. You travel exactly 35 miles down the stretch of highway. Step 3. You pass radar B at 57 miles per hour. And this happens exactly 30 minutes or half an hour after you pass radar A. So at both checkpoints, you were legally under that 60 mile per hour limit.
But here's the gotcha moment. Law enforcement isn't just looking at those two isolated snapshots. They're looking at the entire interval. You traveled 35 miles in exactly 0.5 hours. If we divide your total distance by your total time, 35 divided by 0.5, we get an average speed of 70 miles per hour. And because your average speed over that stretch was 70, mathematical law absolutely guarantees that you must have been traveling exactly 70 miles per hour at some specific, undeniable instant during that trip. You're officially busted.
Section 1. The Mean Value Theorem.
The actual mathematical law that caught our driver is the mean value theorem. To really grasp it, we have to understand the core difference between two types of measurement. First, we have the average rate of change. Graphically, you can think of this as a secant line, a straight line connecting two distinct points on a curve, just like measuring the distance and time between our two radar guns. On the other hand, we have the instantaneous rate of change. This is represented by a tangent line, a line that perfectly grazes the curve at one single specific point. That represents a snapshot of your exact speed in a single instant.
And this brilliant relationship is the entire core of the concept. If you look at a secant line connecting point A and point B, giving us the average, and then check out a tangent line at some point C, well, the mean value theorem guarantees that as long as our curve is smooth and continuous, there will always be at least one point, our point C, where the tangent line is perfectly parallel to the secant line. Parallel lines have the exact same slope, meaning your instantaneous speed at point C was exactly equal to your average speed between A and B.
Section 2. Rolle's Theorem and Foundations.
Now, mathematicians didn't just stumble onto this grand theorem overnight. Back in the late 1600s, Michel Rolle built a crucial stepping stone. Rolle's theorem is essentially a simpler case of the mean value theorem. It says that if a continuous and smooth function starts and ends at the exact same height, meaning the average rate of change is 0, it must have a perfectly flat tangent line somewhere in between. Think of it like throwing a ball straight up into the air and catching it at the exact same height. Because it started and ended at the same place, there absolutely has to be a specific moment at the very peak of its flight where its instantaneous velocity was exactly 0 before it started falling back down.
Mathematically, we express this flat tangent line as the derivative at point C equaling 0. And what's amazing is how mathematicians use this. By taking our original function and cleverly subtracting the secant line from it, we essentially tilt the whole graph so the starting and ending points are sitting at the exact same height, 0. This lets us use Rolle's theorem to mathematically prove the much more complex mean value theorem. We literally use the simple case to prove the universal one.
Section 3. Bacteria, pollution, and applications. Let's pull back from pure theory for a second, because the true beauty of mathematics is how it maps perfectly onto reality. Whether you're in biological engineering, tracking bacteria growth rates, or environmental engineering, modeling air pollution, or civil engineering, analyzing gas mileage, the rule holds entirely true. Any process in the universe with a measurable average must hit that exact average instantaneously at some hidden point. Say you're a biological engineer looking at a highly complex growth chart for a bacterial culture. You can easily calculate the average growth rate over a 24-hour period. But using the mean value theorem, you know for a fact there are specific moments where the instantaneous growth rate perfectly matches that average. By finding those exact moments, you can perfectly time chemical interventions or adjust lab conditions for maximum effectiveness.
Or think about environmental engineering. Your car's dashboard might proudly tell you that you average 30 miles per gallon on a road trip, but in reality, your efficiency is fluctuating constantly based on hills, braking, and accelerating. Engineers analyze these average emissions over time, knowing that the mean value theorem guarantees exact moments where the vehicle is emitting peak pollution. This allows them to significantly better predict and counteract smog in city planning.
Section 4. The mathematical fine print.
Now, mathematics is an incredibly strict discipline, and there are two non-negotiable conditions for the mean value theorem to actually work. First, the function must be continuous on a closed interval. No gaps, no breaks. Obviously, if our speeding car could instantly teleport 35 miles down the road, it wouldn't have an instantaneous speed for us to measure. Second, the function must be differentiable on an open interval. In plain English, no sharp turns and no sudden jagged spikes.
Imagine a graph with a sharp, sudden V shape in the middle, like an absolute value graph. At that exact sharp corner, or cusp, the direction changes so suddenly that there is no single definable tangent line. And because of that one sharp turn, you can absolutely draw a secant line across the graph, but you will never find a tangent line parallel to it. The theorem just breaks completely.
It's honestly a profound lesson in mathematics. One bad point ruins the entire proof. Mathematics demands absolute perfection. Literally just a single point of non-differentiability, just one sharp turn where a derivative cannot be calculated, voids our ability to find that hidden parallel tangent line. The conditions must be perfectly met for the magic to happen.
Section 5. Why this theorem matters.
As we bring this explainer into its grand finale, we have to look at the big picture. Why do mathematicians obsess over a theorem that just tells us something we probably already guessed intuitively? Because this single concept is the underlying foundation for almost all of the advanced tools we use in calculus and engineering. Without the mean value theorem, we literally cannot rigorously prove the first derivative test, the second derivative test, or how graphs curve through concavity. More importantly, it's the absolutely crucial stepping stone used to prove the fundamental theorem of calculus itself, the very core of the discipline.
So the crucial point is captured perfectly in its equation. This is the elegant algebraic translation of everything we've just visually explored with cars, radar guns, and parallel lines. Function of b minus function of a equals the derivative of c times the quantity b minus a.
And if we read this formula in plain English, it genuinely sounds like an undeniable law of the physical world. The difference between your final and initial state is exactly equal to your instantaneous rate of change at some hidden moment, multiplied by the time it took. It forces us to realize that the average of any smooth journey is forever linked to a specific hidden instant of truth.
Which leaves us with a pretty fascinating thought to ponder. If calculating a simple average over time can mathematically prove the exact speed of a car in a hidden, unobserved instant, what other hidden truths of the universe are waiting to be uncovered by simple averages? Calculus isn't just about finding answers, it's about proving the very mechanics of reality itself. Keep questioning, keep learning, and I'll catch you in the next explainer.